about sampling. It will be a bit different from the previous talk. It will be less about hashing. I'm using hashing. Hashing is very subtle to the techniques that I'm going to show you. But it's not really about hashing. It's also not about algorithm. It's about estimation. So just if you lose me at any point, just feel free to ask and stop me. It will make me feel really well that I'm not losing you guys. I'm going to build the stuff as I go. Okay. So sampling. So let's start with sampling one item. Okay, so that's kind of easy. And I can even do it in the streaming model that Graham talked about this morning. So I show you the items one by one. And you get a stream of items. And you want to stay with one item uniformly at random. Whenever you don't even have to know when the stream ends. At any point in time, you have to have one at random, uniformly at random from whatever items you've seen. So that's, there is a very nice way to do it, very old way. So I show you the first item, you take it, it's your sample, you don't have any choice. So I give you the second item, so you flip a coin and with probability half you switch. Right? You discard the one that you have. Then I show you the third one, which is with probability 1/3. You discard the one that you have and switch to this one. So say, you flip a coin now, if it comes up head, and it comes up head with probability 1/3, you switch. So say, I switch, and then so on and so forth. So it's kind of an easy exercise that I'm not going to do to show that at any point in time here you have a uniformly random item. And it's called the wow something, very old by Dieter. But, so let's make life, so there is no hashing so far. But hashing comes into play quickly. Say I give you the items, but now they come with duplications. An item will repeat. You may see the same guy in your stream more than once. But you still want a uniformly random sample from the set of distinct items. So the fact that you see it more than once should not boost the probability that this guy will have not understand. So what do you do? Right, so the previous technique doesn't work. So, so what do you do? So one thing you can do is choose a hash function, say a truly random hash function, and for each item just apply the hash function, get the hash value. And as you go, I show you the items, then you always maintain the smallest, the one that has the smallest hash value. So if it's truly random hash function, then it's easy to see that you would have a uniformly random item from the distinct item that we've seen so far. And I mean, you don't really have to use the truly random hash function. What you need to do that is a meanwise independent family. A family such that if I take a hash function from the family, each guy is equally likely to be a minimum. And there is a lot of theory about those hash families, which I'm not going to talk about. I'm going to assume, I'm going to make my life really easy in this talk. I'm going to assume that the hash value of each item is just a, yeah.
Small. Go back one.
Sure.
I didn't get it. So suppose you had.
So I give you an item, you apply the hash function to the item.
Yes.
You get the value. If it's smaller than the value, so you always keep, I'm sampling one item still, right?
Yes.
I always keep an item.
Yes.
When I see the next one, I compare the hash values of the two. I keep the guy with the minimum hash value in the prefix that I've seen so far, basically.
Okay.
Right? And at any point in time, I have one, which is.
Yeah. So if it was already sampled, then you don't.
Yeah, because I hash them, then identical copies would hash to the same thing and would not affect. The fact that I see them more than once would not affect the minimum. Yeah, so this is a general technique to cope with streaming in which you have duplications. Anyway, about hashing, so I'm going to assume that my hash value for each item is just a uniformly random number at either a 0 or 1. Basically, my use of hashing would be to give independent unique IDs to the items. That's all I would use them for. So the hash value would be uniformly a uniform variable in 0, 1. And I assume that the h values of the different items are independent. I think all we really need is 2 independents. That's it. Okay, so we have seen how to sample one item, right? We just we hash, and we keep the guy with the minimum hash value. Let's try to sample more. Say I want a set of size k items, which are uniformly done. Like among all subsets of size k, I want to uniformly set. So what can I do? Right, so one thing you can do is just take k different hash functions and keep the minimum according to each hash function. This would not necessarily give you k different items. It could be that the same guy would be the minimum with respect to 2 functions. It would give you at most k items. If n is much larger than k, you would probably get k different items. If you want to get exactly k items, you can still use one hash function and take the k smallest guy. Not the smallest, not only the smallest, but the second smallest, the third smallest, k smallest guy. So this actually corresponds to sampling with replacement. Right? And this corresponds to sampling k item without replacement. Right? And here I always stay with a subset of size k. I'm going to stick with this method for the rest of the talk. So my sampling scheme is going to be basically to keep the k smallest items according to some hash function. Okay? And my focus would be on how to use the sample. I play with the sampling scheme a little bit, but the main focus would be how to use the sample to get estimator. And the setting that I'm working at is that I don't really know what you want to, what the query would be when I do the sampling. I want the sampling to be of general use. So later on, somebody would give me a predicate. Say, I want an estimate of the number of IP flows which go to a particular destination IP address or with a particular port or with a particular size. So there is some predicate on some metadata associated with the item that specify a subset, and I want an estimate. I want to develop estimators such that from the sample I could give you an estimate for what you are asking for the subset that satisfies the parameters of the query. I'm going to call this subset the green items just to be brief, but green items could be any subset that you can specify using the metadata. Sometimes it makes sense also to ask for estimating the size of, maybe I don't know when there are these multiplicities, just estimating how many distinct items there were there in total. That's not a trivial problem. Graham is going to talk about that tomorrow, I believe. They have 0 problem. And even that could be very interesting. Just take the sample and give me an estimate of how many, what is n actually? What was the, how many distinct items have you seen? Okay, so let's assume for a second that you know n. You know the number of distinct items. And you want to estimate the total number of some subset, say the green item, from your sample. So this particular setting is very simple. It's very easy to do. Very, very intuitive what you do. Right? You can say what to do. Right? Look at your sample. You have k items, the k smallest guys, according to some hash function. Right? And from this sample, I want to estimate the number of green items in the population, in the large set of distinct items. So what would you do? Yeah.
The quotient of the green items in the sample.
Again?
The quotient of the green items.
Right. So you look at the portion of the green items in your sample and say that, oops, I'm sorry, and say that so the portion of green, G is how many green items are in my sample. K is the size of the sample, G over K is the proportion of green items out of my sample, and I scale it up. If I know n, then I say, well, the same proportion should be at the population. And so this is very intuitive. You can show that the expectation of this, I'm going to show you actually, the expectation of this is really the number of green items, an estimated variance. So let me try to look at this estimate in a slightly different way. And I want to define this notion that is called an adjusted weight that I'm going to use in the rest of the talk. So there is this huge sample space, right? I mean, my sample space, each point in my sample space actually corresponds to an assignment of hash values to all the items, right? This is one assignment of hash values, this is another assignment, and so on and so forth. And once I assign the hash value, my bottom case sample is fixed, right? It's determined, it's the case smallest guy, right? And now think about the green item, one of the items in the subset that you want to estimate. And for each point in my sample space, I'm going to assign an adjusted weight to the green item. So let's look at this point, for example. If the green item is not among the case smallest guy, its adjusted weight is going to be 0. Right? If the green item X is some green item, if it's not in the sample, it's going to be 0. And now there are those points here where the green item is in the sample, and in each of these points, the adjusted weight of this green item is going to be 1 over P, where P is the probability that it's in the sample. P is actually the fraction of these squares. So in P fraction of my sample space, this particular green is going to be my sample. And in this particular point, I'm going to give it an adjusted weight of 1 over P. In this particular simple situation, what's the probability that a particular green item is in my sample? Sample of size k, uniformly random subset of size k, so it's k over n. The probability that a particular green item is in my sample is k over n. So the adjusted weight of a green item is going to be, 1 over P is going to be n over k. It's going to be n over k everywhere where it is in the sample, and when it is not in the sample, it's 0. So this is a general thing, right? I look at an item in the subset that I want to estimate, and when it is sampled, I give it an adjusted weight, which is 1 over the probability that it would be sampled. It's a bit confusing maybe in the beginning. So the property of this adjusted weight is that its expectation is 1, right? With probability P. The adjusted weight is 1 over P. And with probability 1 minus P is 0. Okay, so each green item, the expectation of the adjusted weight of each green item is exactly 1. So, and the estimator is going to be the sum of these adjusted weights. So I'm going to estimate the subpopulation, the subset, by summing the, so when you come to estimate, you have 1 point, right? You have 1 point in the sample set. This is the bottom k that you have sampled. So you're going to sum the adjusted weight of all the items in the subset that you're estimating in this particular point, for this particular sample that you get. And summing these adjusted weights, it's enough to know the sample to sum them all, because they are positive only for the guys that are in the sample. So in this particular simple setting, the sum of the adjusted weight, what is it? It's n over k for each green item in the sample, and 0 for each green item which is not in the sample. So it's like g times n over k. It's exactly the previous intuitive estimate, presented in a very complicated way. Okay, so this is exactly g times n over k. And now you can see that the expectation of this estimator is exactly the size that you want to estimate, right? Because if you take expectation here, And the sum of 1 over p over the green guys in the sample is equal to the sum of the adjusted weights over all green items, because the other ones are just 0. It's positive only on your sample. And by linearity of the expectation, this is just the sum of the expectations of the adjusted weight, and the expectation of each adjusted weight is this calculation that we just did. It's exactly 1. Right? So this actually proves that the estimator is what we call unbiased. The expectation, this is the first property that you may want out of your estimator. You want the expectation of this estimator to be the size that you are trying to estimate. So if I take the average of this estimator over all the points in my sample space, I get exactly the number of green items. All right? And as the set gets larger, it gets to be more and more rapid. Is that okay? I mean, the notion of adjusted weight, you get it, or you want me to repeat anything? Because it's going to. If you didn't get what is adjusted weight, then I. All right. So one problem with this simple thing is that I already mentioned that. So to do this, I assume that you know n. When you come to estimate, you have the sample. You can count how many green items are in the sample by checking the metadata of all of them. But to use this estimator, you also need to know n, the total number of distinct items, which may not be available. So how do we do something like that without knowing n? I just know, so I can count the green items, but I don't have this n to do this g over k times n. It doesn't work anymore, right? And sometimes it's even worse. Sometimes I want to use this technique to estimate n itself. So here is the basic trick that would allow you to do that. So what you're going to do, I'm going to partition this big sample space into subsets. So fix a green item. Now partition the sample space according to the hash values of all the other items. Fix the hash values of all the other items except the hash value of this particular green item. So it looks like. So a point in this sample space is just an assignment of hash values, and I'm going to condition on the hash value assigned to all the elements but one particular item, x. So in each subset in my partition, all the hash values of xj are fixed, except the hash value of some particular item x. Right? So the points here differ just by the hash value of x. All the others are fixed. All right, so now let me. So if you do this conditioning and you look at this subset, and now I ask you, what's the probability, conditioning on the knowledge that my sample is in this particular subset, what's the probability that x is in my sample? In the bottom k, in the smallest k guy. I mean, that's easy, because in each of these points, the hash values of all the other ones are fixed. So all I need to do is to sort the other ones, to look at the k largest among the other ones, right? And if the hash value of x would be smaller than this thing, x would be in the bottom k. And if it's larger than this thing, x is not, right? So in each subset of my probability space, I actually know the probability by which I choose x. Right? So in this subset, h of x should be smaller than the kth largest hash of the xj's in order to be in the sample. And I denote this value hk minus x. Hk minus x is just take all these points, sort them by the hash value, and look at the hash value of the k guy. If the hash value of x is smaller than this, then it would be in the sample, otherwise it's not. So now, how does this help? So what can I do now? So I want an estimator for the number of green items, right? So my goal is actually to give if I am able to give an adjusted weight to the grids, let me do the slide. So we already know this, the probability that X is sampled conditioned on me being in this subset is this HX minus. So now I can give an adjusted weight to X, conditioned on being in this subset. So remember, what is the adjusted weight? The adjusted weight is going to be, if X is not in the sample, it's going to be 0. And if X is in the sample, I want it to be 1 over P, where P is the probability of me being in the sample. Now, I don't know the overall P, because I don't know N. But I know P conditioned, I almost know P, conditioned on my sample being in this subset. Right, what is it? I mean, it's this number, right? If this is 0.7, then the probability is 0, and remember, my hash values are uniformly random at 0, 1. So if the hash of X would be smaller than 0.7, which will happen with probability 0.7, then X is in the sample, otherwise it's not in the sample. So conditioned on being in one of these subsets, I know the probability that X is included. And then I can give it, so the adjusted weight of X is going to be different in each of these subspaces. But in each of these subspaces, the expectation of the adjusted weight is going to be 1. Because conditioned on being the subset, it's P times 1 over P, plus 1 over P, plus 1 minus P times 0. And if I'm unbiased in each subspace, I'm also unbiased overall. So there is one slight thing here. So what would be my estimate? So I give you this point. This is your sample. So what do you need to know now to get me my estimate? The estimate should be the sum of the adjusted weights of all the green items. So the green items that are not in my sample are zeros. They are not a problem. So it's enough to sum the 1 over P over the green items in my sample. So I can count how many green items are in my sample. Now I need to know this P. This P is this HK minus X. Can I know this thing for my sample? This is the kth largest hash value of items different than X. It's not really in my sample. In my sample, I have, when is this number is in my sample? My sample contains the kth smallest guys and everything about them, the hash value, the metadata, and everything. So if X is not in my sample, I actually know this value because it's the kth largest in my sample. But then I don't need it, right? Because if X is not in my sample, the adjusted weight is 0. When X is in my sample, I need this number, but then it's right off mine, right? I have the kth smallest. One of them is X, and among the other one, I only have K minus 1. So I need an additional 1. So all I need to do to apply this scheme is I need to, so this would be my estimator, and in order to know this value when I'm going to estimate, I'm going to keep one additional hash value with my sample. So I'm going to change the sample. So far we just kept the smallest K, and I'm actually going to keep K plus 1, or at least the hash value of the K plus 1 smallest item. I don't need the item, I need the hash value of the item to figure out this probability. Okay, so we keep the bottom K, and so let's conclude this thing because it's very important. So I keep the bottom K and the hash, the K plus 1 smallest hash value. When you look at your sample, you count how many green items are there, and your estimate is going to be, I'm sorry, I'm going backward. Your estimate, so you have this HK plus 1, this HK plus 1 is the same. When X is in the sample, this HK plus 1 is going to be the same as this kth largest among the guys that are not X. So I have this value in my sample, and I'm going to count how many green items are there. This should be k plus 1. This is a typo. And I'm going to multiply the number of green items by 1 over the k plus 1 largest hash value. And this is my estimator. And this is an unbiased estimator for the number of green items. Okay, so this is how I cope with the, yeah.
Wait, I can understand why the shared value of t is k plus 1. Why is the shared value of 1 over hk the same as 1?
So hk is actually p. Hk plus 1 is actually p, conditioned on you being in one of these fixed subsets. So fix the subset. Hk plus 1 is exactly, when x is in the sample, suppose this sample contains x, hk plus 1 is the k plus 1 larger, so it's exactly the kth largest among those that are not x. So it will be exactly this number, which is the probability that x is in the sample conditioned on you being in this particular subset. Okay, so this is not the global peak. This is not the global probability that x is in your sample. This is the probability that x is in your sample conditioned on you being in one of these fixed subsets. No way. So is this okay? So this is how you overcome the fact that you may not know n. And so the term coordinated sampling, which appeared in my title, is actually used for many different things, I think. We usually use it for a situation in which we have more than one set. So far I have one set which I sampled. I had a bottom case sample, and from this bottom case sample I wanted to estimate a certain subset. In many situations you have more than one set. The sets are from the subset of the same global universe. And you may be sampling, so each of these sets can be located somewhere, in a different location. So maybe you can imagine routers in the network, and each router see a different subset of the IP flows, and each router samples the traffic that goes through it independently from the other router. So the set A is the set that router number 1 sees and samples from. The set B is the set that router number 2 sees and samples from. So there are different subsets, and I sampled the same way. So router 1 actually, what router 1 does is applies the hash value, the hash function to each of these IP addresses, and it takes the K flows with smallest hash value, and the same does B. Now, there are two ways now that you can do this. And the difference is whether these routers are going to agree on the hash function or not. So we use the term coordinated sampling when you sample all the subsets using the same hash function. It gives you, for some queries, it gives you a lot of power and a lot of advantage. And I'm going to focus on that in most of the rest of the talk. Okay? So I'm going to assume that, so you have multiple subsets now. Each subset is going to be sampled by the bottom K technique, the K smallest, in a different place, in a different location, but the sampling mechanisms are going to agree on the same hash function. What does that do? It makes an element which was sampled by router A is also likely. What does it mean that router A sampled the guy? It means that the hash value of the guy is small, and then router B is also more likely to sample. Common items are likely to be sampled by both of them with higher probability than what would have been if I would have used different hash functions. Okay? So this gives me an advantage. For example, now you may ask, so I give you, so let me go to this example. I give you the sample of A, the bottom K sketch of A. This is the K smallest, the K smallest IP addresses that went through A. And this is the K smallest with respect to the hash values, IP addresses that went through B. And from these two sketches, I want to estimate now the size of the intersection. I want to know how many IP addresses were seen both by router A and by router B. How do I do that? Yeah. Correct. So I intersect the sample and then what? I can divide, I know K, but what, I don't know the sizes of A and B, I don't know that. I have no clue how many IP addresses. And even if I know the sizes, so all you get is your sample, the bottom K sample, and I give you. So you can actually use the same trick that I did here. Let's try to give an adjusted weight to each IP address. So we want to estimate A intersect B. So for every item in A intersect B, let's try to stick an adjusted weight such that the expectation of this adjusted weight would be 1, right? And then if I sum these adjusted weight, I get an unbiased estimate of the intersection. So I give you the bottom K. These are the bottom K sketch of A. These are the IP addresses with smallest hash value. This is the smallest, second smallest, and so on. And this is the K plus 1 that I also give. And I'm going to give adjusted weight to all the elements in the intersection of A and B. And the adjusted weight of a guy in the intersection is going to be positive only if it is in the intersection of the sample. So I intersect the sample, and if I see an element in both samples, I'm going to give it a positive adjusted weight. Otherwise, the adjusted weight is going to be 0. And I want the average of these values to be exactly 1. Then the scheme would work. Then I get an unbiased estimate of the intersection. So if X is in the intersection of the sample, like this guy here or this guy here, I'm going to give it an adjusted weight which is 1 over P. And what should be P here? Right, for this to be here.
The minimum of the two
Right, but well, in words, so you are ahead of me. So P should be the probability that an element is in the intersection, right? If I give you the sketches and you are able to compute the probability that P is in the intersection of the sketches, then you can do that, right? You can give each element in the intersection, get an adjusted weight of this 1 over P, and then you sum the adjusted weight of everybody in the sample, of all the guys which are in the intersection and in the sample, and you get an unbiased estimate of the quantity. And so P should be the probability that X is in the intersection of the sketches. And I could do it, I could use the same trick that I did here, and I can condition on the ranks of all the other items, which are not X. All the hash value, fix the hash values of everybody except one particular element. And now in this subspace, try to compute the probability, condition on all these hash values being fixed. What's the probability of X being in the sample, in the intersection of the sample? You have fixed all the hash values, this is X. Fix all the hash values of everybody else. And now what's the probability that it's in the intersection? So to be in the intersection, your hash value, to be in this sketch, your hash value should be smaller than HK plus 1. And to be in this sketch, your hash value should be smaller than this, the K plus 1 larger than that guy. And since I'm using the same hash function, right, then I satisfy both conditions if I'm smaller than the smaller of them. So if this is 0.6 and this is 0.8, x would be in the sample with probability 0.6, the smaller of these two. So basically, P is going to be the minimum of this, as you said, and the adjusted weight is going to be, the final estimator, I'm just going to do something like that. I'm going to look how many items I have in the intersection, right? And multiply this by 1 over how many items which are green. Yeah, or here I want to the entire intersection, so it doesn't matter. I'm going to multiply this by 1 over the mean of hk plus 1 blue and the hk plus 1 red. And this is an unbiased estimator for the size of the intersection. Now, what is the advantage of using coordinated sampling? So, where do I gain by using, by having these routers sample with the same hash function? What would have happened if they would have sampled with different hashes? So each one would take this k smallest with respect to some other function. Where does the scheme change? Where does it affect the scheme? I can still do the same thing, right? I can still try to look at the items in the intersection and try to give each one of them an adjusted weight. And the thing that changes is this speed, right? The probability of somebody being in the red sample and the blue sample, now it's not going to be the minimum among these two, right? What should it be? Say, if it's independent, to be in the red sample, I should be smaller than 0.6 with respect to one H function. And then I should be smaller than, say, 0.8 with respect to some other H function. So it's actually, I have to multiply it, right? If it would have been independent, then the probability would have been much, much smaller. And I'm going to show you what's the variance of this adjusted weight in a second. And you would immediately see that the variance goes down as the probability goes up, which is intuitive. Okay. So you can do, it's very common here to give homework, so here you get one. Very similar to the previous one. Anyway. The next step is to generalize everything that I said. So I'm going to show you these ideas through these examples, like the intersection, but it's really much more general. It's for a general subset. The technique works for general subset selection, and so it doesn't have to be the intersection. You can apply it to many, many other predictors. Anyway, suppose now, so far I estimated cardinalities of subset. Like the number of green items or the size of the population entirely, each item counted as one. Now suppose the items are weighted, which is very common, like these IP flows usually have sizes. Right? And often you don't want to know how many different IP addresses the router has seen or that both routers have seen. You want to know the total amount of flow in the selected subset. Right? So think about the weight, the size of the flow, and I want to generalize this scheme such that I can estimate not cardinality of subset, but total size of a subset, in the total sum of the weights of each selected subset. So this is the situation. Each flow has a size, and you can ask what's the total size of the intersection if you have many sets. So let's focus on one set. What's the total size of the green items that router 1 is seeing, for example? So how will you generalize the scheme? So it's a very simple change that you can do, and it works. The adjusted weight was 1 over P if I sample you, and 0 otherwise. So the expectation would be 1. That's good for cardinality, but I want to count it. If I want to count the total weight, I need this to be the weight of the item. So instead of defining the adjusted weight to be 1 over P, I would define it to be the weight over P. If I sample you, and otherwise it's 0. And then I can again sum the adjusted weights of the guys in the selected sum, the green items which are in my sample, and the expectation would be exactly the same. Calculation showed that the expectation would be the total weight of the green items rather than the cardinality of the set. So what's the problem with this? I mean, it works. It gives you an unbiased estimator. But this estimator no, I don't know the weights of the item. An item comes with the weight. I assume now that I know the weight. The items are in one piece. And
High variance?
I vary. Right? I mean, if in the setup that items have weight, you want to sample heavy items with larger probability. Right? So I want to change actually the sampling scheme itself. So far, I took the bottom k was the k smallest in terms of some hash value. My sampling scheme does not use the weights. So everything works, but the variance will be very high because I'm going to miss items which are heavy very easily, and my estimation would be very bad. So again, a minor change would fix it. So I want to change, now I'm not going to change the estimators. I'm going to change the way I sample. I'm not going to take the bottom k in terms of some hash values. I'm going to change it. So what would be a natural way to change the way I sample? I want to sample k items, and I want somehow to be the sampling to be proportional to the weight. Right? So you can generalize the bottom k scheme in various ways. So one, maybe the most natural way to do it. So here, I forgot to show you this. This is important. Let's do this before I show you how to. So this is the variance of this adjusted weight, which I haven't yet calculated. It's very easy to calculate. So the expectation of the adjusted weight is the weight of the item, right? This is the same calculation as here when you put the W here. So the expectation of the adjusted weight. And to get the variance of the adjusted weight, I need to know the expectation of the adjusted weight square, and to subtract the expectation square, which is W x squared. And this is easy, right? This is with probability P. It's Wx over P squared, and with probability 1 minus P is 0. Okay, so this is the calculation that is on the slide here. So if you pull Wx out of the parentheses, you get Wx squared times 1 over P minus 1. So you can see here that as P gets larger, the variance gets smaller, right? And it's especially important if W is very large. Then you want P to be large in general, but in particular you want it to be large when the weight is very large. Because otherwise, if P is small and the weight is very large, this variance is going to be huge. And the total variance of your estimator is just the sum of these variances, because it's at. Okay, so the way to deal with that is to change the sampling scheme and to sample. Okay. So I'm going to, yeah, so far we just hash each item and we take the smallest one according to the hash value. Now I'm going to stick one step in the middle. Instead of using the hash value, I'm going to scale this hash value somehow to mix it up with the weight, such that the weight drives it down to be even smaller. So items with higher weight. So I'm going to take the hash value and translate it to what I call a rank. The rank is going to be a function of this hash value, this uniform ID between 0 and 1, and the weight. And from that on, it's going to work the same. So instead of taking the k smallest with respect to the hash value per se, I'm going to take them with respect to the rank. The k smallest guy with respect to the rank. And that is going to give me a sort of a weighted sample. Now, there are different ways to do it, depending upon how I take the hash and the weight this rank. So one natural way to do it is just to take the hash value and divide it by the weight, right? So this is the first thing that you can do is define the rank of an item to be the hash value divided by the weight. The hash value is still this uniform 0, 1 random variable. And then you can just order the guys by the ranking and take the case model. This is the ranking that Mikkel and others used in priority sampling. Another way to do it, which has its advantages, is to take the weight and take an exponential distribution such that the weight of the item is the parameter of the exponential distribution. So if the item is weight 1, I'm going to take an exponential distribution with parameter 1. If the item is weight 2, I'm going to take an exponential distribution with parameter 2, and so on. So the exponential distribution is going to descend faster as the weight gets higher. And then sample, so if the item has a weight 8, I'm going to take an exponential distribution with parameter 8 and sample the rank from this distribution. Right? And then order the items according to this rank. This is this also, I mean, larger weight is more likely to get smaller rank, right? Because if you have a larger weight, your exponential distribution is going to go much steeper down, so you're more likely to get smaller rank. And you actually can show that using these exponential ranks is equivalent to doing weighted sampling without replacement. So pick the first guy proportional to the weight, right? If big W is the total weight, so I sample the first item with probability Wx over W, and then I take it away, and I sample the next one proportional to the weight from the remaining subset, and so on. This is exactly, doing this exponential ranking is exactly equivalent to that, which is sometimes useful. And computationally, to get these exponential ranks, you can just throw a random variable in 0, 1, and take the natural logarithm of 1 minus that divided by the weight. This is it's easy to see that this is an exponential random variable. Right? So instead of doing H over W, like the simple priority rank, I'm doing something slightly more complicated, and I get this also ranking scheme which is monotone with the weight. Okay? Yeah?
Is the weight unique to the item? You see items 2 times different weights?
I barely hear you.
Is the weight unique to the item, or you see?
Yeah, the weight is an attribute of the item. Each item has its weight. It comes with the weight. When I see the item and I do the sampling, I know the weight and I can get the rank. And I also know the weight when I do the estimation of the guys that in my sample. Okay, so now after we make this change, everything else basically stays the same, right? I can use the same way that I got my previous estimators continues to work, just I'm using the ranks instead of the hash values. So when I do the conditioning, I condition on the ranks of all the items except a single one. And in this subspace, I can usually compute easily the probability of the item being in the sample, and then I can take 1 over the probability. So everything basically works the same. The adjusted weight is going to be, so before it was the weight divided by the probability, and the probability was exactly the hash of the k plus 1 largest guy. Now it's going to be, so fix this subset, right? So in this subset, the ranks of all the items except the rank of x are fixed. So look at the k, the rank, the kth rank in the set without x. This is this would be equal to the k plus one rank that I keep in my sample, like before, and the probability that x is in the sample, for x to be in the sample, I need the rank of x to be smaller than that. The rank of x, if I use priority ranks, which are the simplest, maybe to present, then I need the hash value of x divided by the weight of x to be smaller than this. Okay, and this happens with this probability. This is a uniform. I just transfer this is equivalent to h of x is smaller than the k plus 1 times w. This is the probability. The probability of this happening is the probability of having x in my sample. Okay, so the weight divided by the inclusion probability, which changes now when the items are weighted, and if x is not in the sample, it's 0. And again, I estimate, I look at my sample, and I sum the adjusted weight of all the green items in my sample, and this is going to be an unbiased estimator for the total weight of the green items, which would have much less variance than the previous one. Okay, so here is a. Okay, so far we covered the adjusted weight scheme. We saw how to generalize it to weighted items, and we need to. When we deal with weighted items, we need to sample proportional to the weight, and then use the adjusted weights more or less the same as before. And now there is a common but slightly more complicated scenario in which, and so far I assume that the item has weight, and the weight is fixed, is one fixed weight that's associated with the items. The item has the same, if we are dealing with multiple sets, the item has the same weight in all the sets. But sometimes that's not the case. Sometimes the same item has a different weight in different sets. Think about these routers, and think about the weight of an item in a router as the total flow, the total number of bytes of this particular IP address or flow that went through this router. Then the weight of the flow is not the same. It's different. Every router sees a different fraction of the flow, but it's still the same item, right? The same item, but now it has a weight 1 when it goes through router 1, and weight 2 when router 2 sees the item, and weight 3 when router 3 sees the item. And now I want something like, so what would happen? Each router is going to make its sample independently, usually, because they don't talk to each other when they sample. And then I want to take the samples from the routers and estimate some subset, which is sort of a combination of, or maybe just think about a simple situation in which you want to sum over the flows the maximum size of the flow in each of the routers, or something like that. So first, each router samples, and then you want to do some estimation of a predicate that combines items from the different routers. But now the problem is, so one thing that we wanted coordination. We saw that, for example, for the intersection, it was very good that the routers, when they sample, they use the same hash. But when the weights comes into play, we wanted the sampling to be weighted, right? We wanted to scale down the hash value by the weight before we took the case model. So does these two combine or not? So how would you get both? So each router wants to sample proportional to the weights that it sees, and they also want this. I also want these samples to be coordinated in the sense that an item that is sampled here is more likely to be sampled in the other places as well. So how would you achieve that? So remember what we did with the weights come in. We took the hash value. We scaled it down by the weight. This was the rank, and then we took the kth smallest with respect to rank. So what would be the generalization here to that would give me both coordination and weighted sample. So they could still agree on the hash function, right? The three router would agree on the same hash function, but each router would compute its own rank. How would he compute it? He would take the hash function, which is common to all of them, and it would scale it down by the weight that it sees. Right? So I have the same hash value in all three routers. When they see an item X, they get the same hash value, but router 1 gets R1, which is the hash over W as the rank of the item. Router 2 gets another. So basically, the ranks are different, but the hash values are the same. So that's how you combine both. You get coordination and weighted sampling both at the same time. It's still more likely if an item, if you fix the item, then the ranks are monotone decreasing with the weight. And it's still more likely that if you sample something here, you will also sample it here. But the weights also play their role. You can do the same with the exponential weights as well. And okay, so the situation is as follows. Each router scans its data and makes its sample. It can do it in streaming fashion. And it samples by computing the rank of each item according to this function and keeping the k smallest guy. So now I get a sketch from router A, which is the k guys with smallest ranks in router A, a sketch from router B, and a sketch from router C. And I want to use these sketches to estimate a subset and to ask queries. So this is the situation. You get the sketch of A, the k smallest, and also the k plus 1 smallest rank. You get the sketch from B, the sketch from C. And now let's take an example. It's a very general scheme, but let's just do it through an example. Let's see how we estimate the sum of the maximum, the sum over the flow of the maximum size of the flow in each of the three rows. So basically, for each row, I want the maximum. If it's not there, it's 0. And I want to estimate the sum of this maximum. Just by the sample. Of course, I don't see the entire time. Right? I just see this. I just see this three sketch. Okay, so if I want to stick with my scheme, I have to give an adjusted weight to each item, such that the average of his adjusted weight would be exactly the maximum weight of the item. And then my estimator would be the sum of the adjusted weight for the guys in the sample. If you're not in the sample, your adjusted weight should be 0. And if you're in the sample, your adjusted weight should be positive such that the average would be 1. So I look at my three samples, and the first question that I ask myself is for which items in these three samples I know the maximum. So if somebody was sampled, if somebody appears in the sketch of A, maybe I didn't say it sharp enough. When router 1 samples an item, it only knows W1. So from this sketch, for each item in this sketch, I only know W1. For each item in this sketch, I only know W2, and so on. So if I see an item in all three sketches, then of course I know the maximum. So one way to get an estimator is to just collect all the items in which appear, just intersect the three sketches, and for each item that appear in the intersection of the three sections, give an adjusted weight, which is the maximum weight, divided by the probability that you appear in the three sketches. This would work, but you can actually use more data. I'm not using the maximum out of my sample if I do that. There are more items in these sketches that I know the maximum weight of. Right? It does not have to appear in all. This is where I use coordination. It does not have to appear in all three sketches in order for me to know the maximum. For example, say the item appears only in the blue sketch, but the rank of the item is smaller than the minimum of these rk plus 1. Then I claim that W2, the weight of the item in the blue sketch, which I know, is the maximum weight. It couldn't be that W1 is larger, because if W1 would have been larger, the red rank of the guy should have been smaller than this guy. Because we are using the same hash function, then the three ranks are monotone in the weight, right? So in fact, what I'm saying that for every item, so for this item, for example, this item is harder to use because I see W2, and I'm not sure that W2 is the maximum, right? It could be that W1 is larger, but I still don't see the item in the sample here because it was not large enough to drive the rank below the red RK. But what I'm saying that I can use all the items for which I actually know the maximum weight for all the items in the union of the three samples, such that the smaller rank of the items is smaller than the minimum of these RK plus 1. If you appear in one of the samples, and your rank is small in at least one of the samples, and your rank is smaller than the rank of this guy, you know that the maximum among the weights that you see is the global maximum. And then I can use this item. I can give it a positive adjusted weight, which would allow me to use more items in my sample and would reduce the variance, right? So this is what we do for each item such that the minimum rank of the item is smaller than the minimum of the RK plus 1. I give it an adjusted weight, which is the maximum that I know divided over P. Now what is P? P is exactly the probability that the item would appear in one of these samples with rank smaller than this rank, which you can calculate, and it comes out to be the rank is the hash value divided, the smallest rank of the item is the hash value divided by the maximum weight, and this should be smaller than this minimum in order for the item to satisfy the condition that I mentioned. Okay. So now, we know how to use coordinated sampling to take advantage of the fact that I'm using the same hash function in all places. I know how to deal with weights. But I'm still not using. So one point in all these things is to use the most that you can out of your sample. You did this sampling. So for example, here you saw the difference. I could have used only the items that appear in the intersection of the samples, but I managed to use more items, to give positive adjusted weight to more items, which reduces my variance. And the question is, did I use everything that I can out of my pre-sketches, or there is more information there that I haven't used? That's usually the question that we ask in all these recent papers that I published mostly with the Bitcoin. Did we use everything that we can, or we didn't? And I think here there is more information in the sample that we can use. So the way this scheme worked, I only used items, I only gave positive adjusted weight to items for which I knew the maximum. If I know the maximum exactly, I collected all the items for which I know the maximum exactly, and all these items got positive adjusted weight. So if I want to use these inverse probability estimators, then actually I use the most that I can, I think. But what about other items? So remember this, let's see an example here. I took the third one out just to simplify the description. But so let's look at this example. There is only maximum of two sets here. And you see this item appears in the red sketch because its rank is smaller than the K plus 9. It appears in the blue sketch, I'm sorry, and it doesn't appear in the red sketch because its rank was larger than the K plus 1 larger rank. From the fact that the rank, from the picture that I draw, you can deduce that the weight of this, W1 is actually larger than W2, right? Because once I fix the item, the lengths are, the hash value is the same, so the lengths are monotonic, inversely monotonic in a way. So I see W2, right? Because it's in the blue sample. And the rank of W2 is not smaller than this red guy, so I'm not sure that I see the maximum. It could be the W1 is large. So the scheme that I showed you just doesn't use this item. It doesn't use the fact that I know W2. But W2 is information that I can use because it gives me information on the maximum. It gives me a lower bound on the maximum. I know that the maximum is at least as large as W2. Even though I don't know it exactly, I have partial information about the quantity of the sample. So this inverse probability estimator, this Robbins-Thomson estimator, cannot deal with partial information. You have to find some, you have to generalize them. But there is a way to use this partial information. So for example, let me just show you briefly what you can do to use the partial information. So let's focus on this item. The hash value of this item is in the range 0, 1. And as the hash value of the items gets smaller, the ranks also get smaller, and the item would start showing up in the sample. When the hash value of the item is really large, I don't see the item, I don't see it in any of the samples. So when I start reducing that, at some point, when the hash value of the item is equal to this RK plus 1 times the weight, blue weight of the item would show up in the blue sample. And at this point, I already know W2. And I can give I can start giving an estimate. I can say that I can take W2 and divide it by the probability. This is the probability that the item is in the blue sample. So I can give an estimate, which is W2 divided. I see W2. I know that the maximum is at least W2. So I give the item an adjusted weight, which would be correct if the maximum would have been W2. So once the items show up in any of the samples, I start giving a positive adjusted weight, which is conservative. I don't know the maximum, but I know a lower bound, so I assume that the maximum is the lower bound. And I give an adjusted weight, which would be true if the maximum is the lower bound. But what if W1 is larger? And at some point, when the hash value is smaller and the rank is sufficiently small, W2 would show up in the red sample as well. I would see them both, right? For some point in my probability space, I would see both W2 and W1. And then I'll figure out that W1 is the maximum and W2 was too small. And then I would do the correction. In this part of the probability space, I would actually give an estimate which is larger to compensate for the smaller estimate that I've given in this one. So you can follow I'm not going to go through this calculation, but by solving this equation, you get the number that you should give the adjusted weight, if you want, that you should give this item when you see both W1 and W2, so that your total estimate would be unbiased. The average of these over the entire probability space would be exactly the maximum. And this is actually very general. You can generalize that, and you can prove sort of variance optimality. You need to for a particular notion of optimality that we can define. We can prove that this is constant competitive and stuff like that. And this is just an example that shows you which information in the sample we were after in all these papers that appear in the end. And for detail, you can take a look at those things. Any questions so far? So let me just show you another thing you can do with bottom K samples, and another place where there is information hidden in the sample. This is actually maybe the first setting in which we did So suppose we have a graph. Okay? This is another scenario in which we have multiple sets, and we want to sample from all the sets in a coordinated fashion, just that the sets are not arbitrary sort of sets that routers see. They are structure sets that are defined by an underlying graph. So suppose we have a graph. This is a graph of a metric space, it doesn't matter. And focus on a particular vertex. And let's say that I want a sample, a bottom case sample, from all the neighborhoods of this vertex. Right? So pick the vertex, pick some distance. There is a ball of this distance around this vertex. Inside the ball there are many other vertices. And I want to sample those other vertices. They may have weight or they may not have weight. But I want a bottom case sketch of the set in any ball around this vertex. So this is easy to do. I mean, just every vertex now draw a random rank. You map each vertex to a random variable at 0, 1. You divide by the weight, if there is weight, or if there isn't weight, the hash value is the rank. And now you start drawing this ball. And when the ball is of this, when the ball is too small, so say I want say my k is equal to 3, meaning I want the k is the bottom k is the number of items that I want in my sample. So say I want a sample of size 3 from each ball, meaning I want the 3 vertices of smallest rank from each ball around V. Okay, so when the ball is small, it contains less than 3 vertices, and I have to take these 3 vertices. I don't have enough vertices to sample. So this red guy must be in this sketch, and then this blue guy and the green guy, they must be here. Now, when you go up with the values, so now you have to take the k smallest guy among these 4. Right? So you just look at the rank of this guy, and you check if it's smaller than the third largest here. So they are sorted here. This is the smallest, second smallest, and third smallest. If the rank of this guy is larger than this rank, then these 3 are the bottom 3 also in this ball, right? So you don't have to add anything. But if the rank of this guy is smaller than this rank, then in the bottom 3 guy of this ball, you should have this guy, right? So you add it. So I go up this ball, and every time I scan a new vertex, I check if it's among the bottom 3 in this ball. So now I compare the rank of this guy to the rank of this guy. If this guy would be smaller, then I would just add, because it belongs to the every vertex that is among the 3 smallest in any ball I want to collect. So I go the ball. When I hit a vertex, I check if it's smaller than the 3 smallest in the ball that I had so far, I add it. And eventually, I accumulate this large set that we call the all distances sketch, because it's a bottom 3 sketch of every distance. And now there are many nice things that you can do with these all distance sketches. This is the last one that is added. So the first thing that I can do, say you give me, so say I calculated the bottom, the ADS sketch of all the vertices, and now you give me a vertex and you ask me how many, the graph does not exist anymore. Maybe I didn't give it, and I can throw away the graph. I can just take the sketches, and from this sketch I can estimate how many vertices. So you give me a vertex and you give me a radius, and I can estimate how many vertices are in this ball without doing the Dijkstra or whatever, without looking at the graph again. How do I do it? So one way to do it is to extract. So this collection of vertices contain the 3 smallest in this ball. So I can find the 3 smallest in this ball. And I can do the same thing that I did here. Take the 4th rank, and the adjusted weight is 1 over the rk plus 1, and multiply it by 3. And this would be an unbiased estimator to the number of vertices in this ball. The same estimator that you've seen before applied to the bottom case sketch in this ball. So from these ADS sketches, you can estimate how many vertices are at certain distance from any vertex. And the advantage is that the size of these sketches is really quite small. So what's the size of this ADS sketch? Okay, so remember what we did. We sort of went through this ball and added the vertex if it was among the k smallest in the ball. So what's the probability that the next vertex gets into the sketch? So the ith vertex gets into the sketch if it's among the k smallest, if it's one of the k smallest, among the first I, order the vertices according to the distance from V. And the ith vertex would be in this sketch if it's among the k smallest out of this first I. So the probability that if the ranks are random and 0, 1, the probability that the ith vertex get into the sketch is k over I. The minimum of 1 and k over I, this could be, for the first three, they go into the sketch for sure, right? And the sum of this thing is order of k ln n. So if k is small, like 3 or 10 or 100, this is about order of log n for each vertex. And if I want it for all the vertices, it's n log n. And the graph could be quadratic in size. So it's a summary, it's almost linear size summary of the graph, from which you can estimate the size of every neighborhood around every vertex. And another thing you can ask yourself about this sketch, so the way I used it for the last thing I'm going to say, so just to show you that how you can find more information in your sample, again, in this different context now. Yeah.
What if you have ranks in the vertices? So for in this case, if the ranks were growing as you went out, then you would have more than k, right?
In the weighted case, you mean?
Yeah.
Yeah.
But can you say something actually you do for all the vertices?
Yeah, I'm not sure about this in the weighted case. I have to think about it. Yeah, with weights, it may be a problem. So the way I did the estimation is, so suppose you give me a ball and you ask me how many to estimate how many vertices are in this ball. Then the way I did it before, I extracted from this thing the bottom k sketch of this ball. Right? Just take the three smallest guys in this ball are in this sketch, because I have the three smallest in every ball. And I just apply the regular machinery for the bottom three estimation from before. But actually here I can do, so the question is, if this is optimal in the sense that I'm using all the information that I have in the sample, or there is some information in the sample that I haven't used. So obviously all these points are in this ball, right? And I've used only 3 of them. I just extracted when the ball is large, the ADS contain many more vertices in the ball than the bottom K, right? And I'm not using them, and I could have used them. So the way I could use them is I could assign adjusted weight to all the vertices in the ADS sketch. And the way to do that, so here so the way I estimated here, first I extracted the bottom 3 sketch for the ball, and then I assigned adjusted weight only to these 3 items. I can actually assign adjusted weight to all the items, and the way to do it, when you compute the ADS sketch, I go this ball, and I put the item in the sketch with certain probability. The probability that the item gets into the sketch is the probability that its rank is smaller than the kth largest so far. Right? So I have an item, I know, conditioned on all the other ranks. So fix the ranks of all the vertices except of this item, of this particular item, Now you know exactly the inclusion probability. You know that the item would get into the sketch if its rank is smaller than the case lowest out. So you can give it an adjusted weight. Right? So the adjusted weight of this item is going to be 1 because it's for sure in the sample. The same for the second one, the same for the third one. But now it gets interesting. This guy doesn't get into the sketch because this predicates fail. But this guy gets into the sketch. I check this, and it comes out to be 2. And the item gets into the sketch. And now I can give it an adjusted weight. Because I know if you fix everything except the rank of this guy, you know that it would get into the sketch exactly if this predicate succeeded. It would succeed with probability, exactly this probability. Right? So you can give it an adjusted weight, which is 1 over the rank of the guy that it competed with. So as you accumulate the ADS sketch, you can give adjusted weight to everybody. And now when you come to, so everybody gets an adjusted weight, and now when you come to do the query that I did before, you can just sum up the adjusted weight of everybody in your board, not just the bottom 3 in your board. And if you compute the variance, this trick actually reduces the variance by a factor of 2, which could be significant. So this is another example in which, if you think about it carefully, you can use more out of your sample. Anyway, I think I'll stop here. There's been too much already. This is some of the recent papers that I sort of touched. I didn't really cover anything, any substantial fraction of any of them. And this is all their relevant stuff in those. Any questions?
You just showed us how to estimate the size of a particular ball which had a radius d, but I didn't understand how d entered into your calculation.
D doesn't. D comes into in query time.
Yes.
When I do the sampling, okay, so D gets into my calculation by, so it depends, I showed 2 estimators, but you give me D, and the first estimator, I just go over all the vertices in my sketch, and I pick only those that are a distance D from the guy.
You keep the distances as well as the vertices.
Yes.
Right.
Okay.
I have to keep the distances, right, exactly. Any other questions? So there were a few exercises in this presentation which are directly related to the slides before that. It's another, if I did intersection and then I ask you to do the difference, which is very, very similar. So if you really want to understand this better, just go through the presentation and try to do these exercises. They should be doable just based upon this stuff, not looking at the papers or anything.